Alrighty, hi everyone. We can get started. How are we feeling? Okay, good, bad, indifferent. Okay, well, hopefully after this, we'll feel a little less stressed and a little less awful about the content. I looked at the Google form I sent out. For a couple of people filled it out with some good questions and just some good things they wanted to look at. So I'll kind of base most of this off of that. Again, I had the practice problems put up Friday, I believe they were. They should be challenging. This is going to probably be harder than what you will see on your final. So if you can do these, those are really, really good. I did use some like AP level questions for an AP exam on them that are kind of more in depth and have a couple of steps with them. So I should be posting that answer key along with this Zoom recording and any notes that we take today when all of that is ready and after this. So look for that by the latest end of the day today, but you should have that for today and tomorrow to study from. But based off of the Google form, I do see a couple of like specific questions that you want to go over. So I think I will go over those specific questions. They do cover a lot of topics that like were mentioned in the Google form. And then if we have any extra, and then when we have extra time, then I can take some more questions from y'all and kind of just tailor that towards what you have to do. If you have any questions at all throughout this, please put them in the chat. I'm happy to answer them there. Or you can just unmute yourself and I'm happy to just take your question that way. Alrighty, any questions for me before we get started? Just general questions or specific questions? In terms of what you should study, what you think the exam is going to look like, anything like that. So I personally do not know anything about the exam. I just know that it is online like your past ones have been. But in terms of content questions and stuff like that, I do not know anything. Like I don't know what topic she's using for your exam. I just know that it will cover everything we've done this year. Okay. Okay, so we had a couple. So when we did this last year, all of the exams were, and by last year I mean when I did this in the fall, all of our exams had 8 multiple choice and then 6 short answer, and then your final was 40 multiple choice questions. But you have 50 minutes to do like your in-class exams, and then you have 2 hours to do your final exam. So just think about doubling whatever content you may see. So if you usually have 8 multiple choice, then you're probably going to have 16 multiple choice. If you usually have 8 short answer, then you're going to have 16 short answer, something like that. Right? It's going to be that same kind of length and that same kind of breakdown in content with all of them. Someone asked me any advice on how to properly study for the exam. I think that's a very good question to ask. I think you really have to know yourself in order to best properly answer. For me, I learned a lot through getting things wrong and like actually doing problems. So that's why I give a lot of practice problems, because that's for me, I can tell that like, okay, I either know this or I don't, because I can read the question, know what I have to do or anything like that. So I think practice problems are a really good way to understand and really study your questions. I think it's really good if you do learn that way to also kind of create your own questions. A lot of the time I make up questions on the spot, and that's something that you can do where you're like, okay, I'm going to solve for this unknown. Or then if you have a question given to you, solve for it backwards, right? Try to find a different unknown based off of the information you have. Other than that, I think it's important to look at just like all of your notes. I know that's like really hard to do. But like just go through them and then write down the big topics, right? If you're like, okay, this was calorimetry, or this was enthalpy, this was entropy, right? Don't try and write down everything, but try and like group things into bigger topics. And that way you're like, okay, these are the things I need to know. And then you can kind of like either write down or ask questions to yourself or to your friends, like, what do I know about these topics? And what are the important things to know about these topics? And then lastly, something I did when I was taking Gen Chem in undergrad is a friend and I would kind of take a day's worth of notes, and we would go in and just look at the PowerPoint together and then just start asking each other questions about it. That way you're like looking at the notes, having to come up with the answer based off of the notes, having to come up with a question based off of notes. And then that kind of helps you understand all that information when you speak it out loud while also reading it and everything like that. So to recap, just practice problems I think are super good. And then if you have a buddy or someone that you can study with, I think that's also very helpful. And then someone said, Dr. Altimo said 30 to 35 questions, which I think is very typical for a final. So I'm assuming some of them will be short answer, some of them will be multiple choice, but it'll be, right, if your in-class exams are mostly multiple choice, then your final exam will mostly be multiple choice. Or like drop down and stuff like that. Okay, anything else before we get started? I hope that was helpful in terms of how to study. Okay, let's start off with a little calorimetry question. This is based off of the Google form question. Okay, so for this question, we have how much energy in kilojoules is required to change the temperature of 325 grams of aluminum from 32 degrees Celsius to 815 degrees Celsius. And our specific heat is 0.897 joules per gram per Kelvin. Okay, so can anyone tell me what like topic or general idea this would fall under?
MCAT.
Yep. Yep, so this is going to be calorimetry. Right, this is a calorimetry type question. And what equation do we usually look for, or a type of equation that we usually look for in calorimetry? MCAT. And what does that equal? What is, yep, perfect. It's going to be equal to Q. So Q here is going to be our heat. MC delta T is our mass, specific heat, and change in temperature respectively. Okay, so when we're looking for how much energy, what letter are we solving for in MCAT? Good, we're looking for Q here. Okay, so if we're going to set this up, we say Q is equal to, what's our mass? Good. Yep, 325. That's in grams. What's our C? Awesome, 0.897. This is joules per gram times Kelvin. And then what's our delta T? Okay. And what units is delta T in? Okay, awesome. Great job, or great question, Sam. So if we're looking between our specific heat and then our temperature, this is in Kelvin. This is in degrees Celsius. But if we were to change it to degrees Celsius, you would take 815 plus 273, and we would take 32 plus 273. But then we would still subtract them, right? So either way, whether you add 273 or you don't add 273, the change is going to stay the same for both of them. So here we can keep it in degrees Celsius, but you should always look to make sure that your units line up. Does it make sense why we can keep it in degrees Celsius and not have to, and we don't have to change it? Okay, so if you were to take 815 and change it to Kelvin, we would take 815 plus 273. Sorry. And we get 1,088. And then if we take 32 and 273, then we get 305. If we subtract this, we get 783. But if we subtract 815 and 32, we also get 783. Okay, so since we're changing the number by 273 for both of them, and then subtracting, right, we're adding and subtracting, then we don't have to change it. No, it's not always like this. If you're in gas laws and you have a degree Celsius, you always have to change it to Kelvin. That one you're adding 273 and then multiplying and dividing by stuff, so those operations don't cancel out. But here, since we're adding and then subtracting, those will cancel. But if it's gas laws, you always, always, always have to change it to Kelvin. Okay, does that make sense why we can keep this one in degrees Celsius right now? When in doubt, if you're nervous, just always change it to match units. And then you would have no problem. But either way, this turns into 783. So then we can say that Q is equal to 325 grams. And then what is Q going to equal?
That would be so in joules, joules would be if it's in kilojoules, would be 228.26 for also.
Awesome. So we have 228.264, but when we use this, it's in joules. So in order to change it to kilojoules, we know that 1,000 joules is in 1 kilojoule. So we get 228 kilojoules. I would keep it to 3 sig figs since our mass is in 3 sig figs and our specific heat is in 3 sig figs. If you change it to Kelvin, you would have, yeah. So in 325, we have 3 sig figs because we have all non-zero numbers. We have 3 sig figs in 0.897 because after the decimal point, we go until we see the first non-zero, which is going to be 8. So all of those are significant. If we're just looking at 32, this would have 2 sig figs, and this would have 3 sig figs. Okay, I'll just talk about sig figs as we go through all of the problems that we do today. And hopefully that will help with the review as well. But for this, I would say 2 sig figs, which would be 2, 2, 8, since all of those are non-zero numbers. Okay, any questions on this one here? Okay. I saw a lot of responses, or I saw a couple of responses just for like Lewis structures and stuff. So we can go over a brief review of all of that. Okay, so for this one, we have which of the following molecules is polar? You have CCl4, SF4, SO3, Br2, and BCl3. Okay, whenever we look for, or I guess, can someone tell me, when we're doing a polar molecule, or you ask if something is polar, what do we need to look at? What's important for determining? Yeah, awesome. Your symmetry, valence electrons, Lewis structure. Awesome. All of those are perfect. So we're looking for your symmetry. We're looking at the Lewis structure. We're looking at valence electrons. What's up? What determines, so let's say something is non-symmetrical, or let's even, what determines polarity? What do we look at the difference between to determine if something's polar or non-polar? Okay, we're looking for things not canceling out. Angles is good. Awesome. Awesome. Electronegativity is the word I was looking for. Electronegativity is super, super, super important, right? All of the ones that are listed in the chat are also important, but electronegativity is what's going to determine if a bond is polar. And if a bond is polar, that might make a whole molecule polar. What's the most electronegative element on the periodic table? Awesome. Fluorine is going to be your most electronegative. What's our trend as we go across the periodic table? Good. What happens as we go down the periodic table? Awesome. Awesome. Okay, so as we go across the periodic table, you are going to increase your electronegativity. So oxygen next to fluorine is going to be less electronegative than fluorine. And then as we go down our periodic table, we're going to be decreasing electronegativity. So potassium is going to be less electronegative than sodium. Okay, so the most electronegative is fluorine in the top right corner, and then your least electronegative is francium in the bottom left corner. Okay, so when we're looking at this question, we say which of the following is polar. We need to look at our Lewis structures in order to determine if the whole molecule is polar. Okay, so for CCl3, what atom is going to go in the center? Good, carbon's going to go in the center. How many bonds do we put around that carbon? Good, we're going to have 4. And how many electrons does one bond count for? Good, we have 2 electrons. So how many electrons did we use during this one? Good, we used 8. Okay, how many valence electrons does chlorine have? We have 7 valence electrons for chlorine. How many chlorine atoms do we have? 4. So we have 28 total electrons from chlorine. How many valence electrons does carbon have? Good. Carbon also has 4. We only have 1 from those, so we have 4 here. So we have 32 total electrons. We just used 8. So how many do we have left over? Good. So now we have 24 electrons left over. What goes on the end of those carbon bonds? Awesome. Yep. Cl will go on the rest of these. And then what do we need to put around Cl? Good, lone pairs. Okay, and I'll tell you now that we use all 24 electrons when we do these chlorines. So this is completely done. Your carbon has 8 electrons from its 4 bonds that it makes, completing its octet. And then chlorine has 8 electrons between the 1 pair and the 3 lone pairs. And so that also completes its octet. So would we describe this structure as polar, this whole molecule as polar or nonpolar? It should be nonpolar, right? The whole molecule is nonpolar. What about the bond between carbon and chlorine? Is that polar? I have 1 person for yes. Do we agree? Yes, I agree as well. Which one's more electronegative, that chlorine or that carbon? Good. Your chlorine's more electronegative, so your dipole is going to point towards the chlorine. And then your positive end goes by that carbon. Okay. So CCl4 is not our correct answer.
when thinking about electronegativity, we be expected to like think about it in sense of periodic trends. So, like undefined right there.
Like which one's more electronegative? So
Yes.
if we look at fluorine in the periodic table,
Yeah.
chlorine is right underneath it, where carbon is 4 atoms away. So since
Yes.
chlorine's closer to fluorine, that one's going to be higher in electronegativity than chlorine. Or
That's
then
what I was talking about the trend. But honestly, I think like on 5 exams, you've been given actually been given that electronegativity basically, so probably going to be that way.
yeah, so I think it's so they might also give you the values of your electronegativity as well as also, and that'll also help you with your electronegativity differences. Sorry, that means whole. This is whole. Okay. So so which has more effect going up or to the right? It should be in terms of size, your going down the periodic table is going to affect your size more than going across. So you can assume the same thing for electronegativity as well. And then we determined it was nonpolar because all of our dipoles are going to point out. And so it looks symmetrical on all the sides. Yep, so symmetrical structures are nonpolar. Okay, so that's kind of a review of how you do a Lewis structure. What would your Lewis structure look like for SF4? What goes in the center? Good, we have S. We're going to make 4 bonds with F. We have 34 total electrons here. How many do we use when we fill our fluorines? So we have 24, we used 8. So we're left with 2. Where do those 2 go? Yep, lone pairs go to the S. So it doesn't matter. It doesn't matter whether, like, if you're just drawing a Lewis structure, it doesn't matter how you place your fluorines or how you place any of your molecules. I could have done the chlorine as an X as well. I just decided to switch it up and try and save some space. It does not matter if you draw it across or an X or anything like that. Okay, so we put our lone pair on our S. So now we're left with 0. So what about this structure? Is this going to be polar or non-polar? And why do we say it's polar? Good, awesome. So this lone pair on the sulfur is what causes your symmetry of your structure to be thrown off. Your lone pairs take up more space than bonded molecules or bonded electrons. And so that's going to distort the shape of your structure. Does anyone know what the shape of this structure is? Good. This is your molecular geometry. Does anyone know what your electron domain geometry shape is? Yep. Okay, so your electron domain geometry is your trigonal pyramidal. This is like the umbrella term for having 5 electron domains around your central atom. And then your specific, or what the molecule actually looks like, is your molecular geometry shape. And that one's going to be seesaw. Okay, but this is your polar molecule. Any questions here? Okay. Your other 2 structures, or your other 3, just to quickly go through them. I think SO3, sorry, your SO3 should have a 2- on this. So this looks like this. Your BR is going to be bonded to BR. And then your BCl3 is an exception where boron only likes to make 3 bonds. And so its octet is filled when it has 6. So it technically has like a it's not a complete octet, but it still is happy like it would be an octet. You do double bonds if your formal charges are wrong, or if you like run out of electrons and you don't have enough to put them on the central atom, right? So if we were to just do that SO3 2- structure, you would see that if you draw 1 bond to each of your oxygens, they would all have a full octet, but then your S would only have 6 electrons. So you take one of those lone pairs and turn it into a double bond, and then your S turns into a complete octet, and then your other atoms also have a full octet as well. Does that make sense on why we do the double bonds? So Zeke, just for the for boron, that's just one that you need to know. Boron only makes 3 bonds. Beryllium only makes 2 bonds. And then anything in the 3rd period or below can make a expanded octet, so it can have more than 8. But carbon, nitrogen, oxygen, fluorine will never make more than 8 bonds, or have more than 8 electrons, excuse me. Right, so for the BCl3, we don't want to take one of those lone pairs on the chlorine and make it a double bond, because then boron is actually less happy with 8 than rather if it had 6. What other questions do we have on this one? So SO3 would not be polar, because what does SO3 experience with this structure where we have 2 single bonds and 1 double bond? What can it do? What other structures are present? What do we call that? Begins with an R. Orbitals don't usually tell you if something is polar or not. That just more has to do with hybridization. You're really going to determine something is polar based off of the shape of the Lewis structure and then the difference in electronegativity. So to go off of Diego's question, SO3 would be nonpolar. because this experiences resonance. And so we could have a structure that looked like this. Or we could have a structure that looks like this. Right, so all of those are in play. And so it might look like the top, the middle, or the right at any time. And so therefore they're all going to be like average out to be one total structure. And then therefore it's nonpolar. Does that make sense for resonance nonpolar stuff of SO3 2-? Okay, awesome. I did ask for someone to go over hybridization. And so we can do that based off of 3 of these structures here. So I'm just going to write this one more time. So we have okay, so for hybridization, you want to look at how many electron domains are around the central atom. Okay. How many electron domains are around carbon in CCl4? Yes. Yep. We have 4 electron domains, right? It can be either a lone pair or a bonded electron. How many electron domains are around SF4? Good. And how many around SO3? Awesome. Okay. So whether you have 4 or 5 or 3, that's going to be how many total orbitals you want in your hybridization or in your hybrid orbitals. How many s orbitals can we have? How many s orbitals are there? We can have 1 s orbital. Your 1 s orbital can hold 2 electrons, but there's only 1 s orbital. So your s will always be your first hybrid orbital you have. How many p orbitals are there? Good. There's 3 p orbitals. We have 1 s orbital, and we have 3 p orbitals. How many d orbitals can we have? Good. We can have 5 d orbitals. Okay. So if we use 1 orbital with our s, we need 3 more orbitals in order to get to 4. What are we going to use in order to get to 3, or in order to get to a total of 4 orbitals? Good. We can use sp. And then we're going to use 3 of those p orbitals. Okay. Because if we look at the exponent, right, we have s to the 1, p to the 3. If we add up 1 and 3, we get 4 total orbitals, and that's going to match our electron domains. So you want sp3 for this one. that make sense why it's sp3? Okay. Whenever you have an electron domain of 4, it'll always be sp3. What about SF4? How many total orbitals do we need? We need 5 total orbitals. So we're going to use 1 from our S. How many from the P? Good. 3P. And how many for the D? Yep. 1D. Awesome. Okay. And then what's going to be our SO3? What's going to be that hybridization on the S? Awesome. This one will be sp2 because we need 3 total orbitals. So you have 1 S and 2 P orbitals. Does that clear up hybridization? And that's always for the central atom. So we can talk about the f orbital, but we won't talk about it for hybridization. The F just comes into play for the electron configuration. So Sam, the electron configuration this is when you do 1s2, 2s2, 2p6, 3s1, or 3s2, 3p6, 4s2, and stuff like that. The electron configuration tells you information about the electrons of the atom. So you can always use them for the noble gases. Like you don't have to pick which one to use unless it tells you to, right? You can, if it says in noble gas notation, write the electron configuration, then you want to use the noble gas. But you can always use either one. It's not gonna it's not gonna hurt you to use the noble gas. It's not gonna hurt you to write it all out. You just want to make sure that the question isn't asking for a specific one. Yep. Okay, anything else about Lewis structures, hybridization, resonance, polarity, electron configurations, anything like that? Okay. Okay, let's talk a little bit about, we'll do one. Let's do one rate question and then we'll talk about like chapter 12 stuff. Okay. So for this question, we have the rate of appearance of Br2 is 0.180 molarity over second. We have what is the rate of disappearance of NOR gas. This is your rates chapter, or kinetics, which I believe is 10 or 11, if I remember correctly. I might be lying. Okay, so what do we need to know about this chapter, or for this question? We know that your rate of disappearance is going to be stoichiometrically equivalent for your rate of appearance for your reactant or for your products. So this is like that one graph that your notes have where it's like, okay, this is concentration on this side. I'm sorry. Concentration on this side. And then time on this side. So at 0 time point, you have no products. And so your one product will come like this. And then your other product will come like this. And then your reactants, you're going to have a lot of reactants and then decrease your reactants over time until it finds equilibrium. Okay, and like this point here, this is your equilibrium. Okay, this is what that is referring to. When we look at rate of appearance or rate of disappearance, it's just talking about reactants getting used and products being produced. So whenever we look at this, this is the delta or the change in concentration of like A over T, where your delta concentration of A over T is your rate component. And that's a reactant is equal to the delta concentration of product over T, again, the rate of appearance. Your coefficient, or the 2 in front of your NOBR and your NO, is also used in your rate. This is saying that your, right, and there's a 1 here. This is saying that your rate of your reactant disappearing is twice as fast as the rate of appearance of your BR2. Because for every 2 moles of your NOBR that you are consuming, you're only producing 1 mole of your bromine. Yes, that's a negative next to the delta. Okay, so if we were to do this question, we know that the rate of appearance of your BR2 is 0.180, and you're looking for this negative delta H component or negative delta A component, which would be your change in concentration of NOBR over time times 1/2. Because in order to get those to be the same, you need to take the reciprocal of your coefficient. So this portion here is the x that we're solving for. So if you plug that in, it's just 1/2 times x is equal to 0.180, and this is 0.360 units of molarity over second. What questions do we have about this one? Yep, awesome. So this should also be negative 0.360 molarity over second as your final answer. So the 1/2, yep, it's negative because the reactants are used. So your 1/2 comes from the coefficient in your equation. So if you had something where it was like 3A plus 4B goes to 2C, it would be 1/3 change in concentration of A over T, which is equal to -1/4 change in concentration of B over T, which is equal to 1/2 the change in concentration of C over T. Okay, so it always is that reciprocal of the coefficient in front of your reactant or product. Any questions on this? Yep, reactants are negative and products are positive. And so the rate of disappearance is -0.360 because delta is always going to be final minus initial. So if you start off with 1, then you might have, okay, 0.75 minus 1, right? Final is your final concentration, initial will be negative. So your rate will be negative. Yep, disappearance should be always negative. Any other questions? Yes, yep, there should be an equal sign between B and A because we're looking at how our rates can all be equal to each other. So we're saying the rate, right? So it's like -1/3 concentration of A over T is also going to be equal to 1/2 the delta concentration of C over T. Those are all saying that the rates of all of those things happening are equal there. I don't know if there are problems on OWL. There might be 1 or 2. Yep, great job, Gabriel. So that rate of appearance of NO would also be 0.360 because their molar ratios are the same. Awesome. Yep, that's perfect. Exactly it. Okay, anything else so far? Okay. Let's look at some of the like chapter 12 stuff. So we can start off with Le Chatelier's principle. Yeah, my practice problems can be used as a practice exam. They will be slightly harder than whenever you're going to see on your final, but that's definitely a good place to start so that you like really, I tried to get a lot of like, try to do all of the chapters if possible. So that's definitely a good thing that you could treat. Okay, so looking at Le Chatelier's principle, this is going to determine how equilibrium is affected and how, like, what's going to happen if equilibrium is disturbed. So this is going to be changes in equilibrium and what results from that. Okay, so let's just take a general chemical equation. We can have A plus B goes to C plus D. And we're going to say the delta H of this reaction is positive. Good. Yep. So this is an endothermic reaction. Okay. But going over Le Chatelier's, I want to know if I increase the amount of A I have at equilibrium, what's going to happen to my reaction? If I increase A, do we make more reactants or do we make more products? Good, we're going to make more products, right? I'm increasing the amount of A, so I have to shift my whole reaction to the right-hand side. Okay, I kind of think about this. I told a couple people in class when they asked, like visually what this looks like for me. So I kind of think of like, okay, I'm making a mountain here. And so in order to decrease that mountain, I need to like push it out. I need to fill this in over on this side so that that mountain goes and is no longer a mountain. Yep, this is because of equilibrium. So I should have a reverse arrow as well. Okay, so that, right, I increase that mountain, so it needs to fall down the mountain in order to return back to equilibrium. Okay. What happens if I decrease my amount of C? This is like scenario 1. Scenario 2 is I'm decreasing C. What do I do? Good, you're going to decrease reactants. We're still, again, going to shift to the right. Right now, this time I have a valley where C is. And so now I need to make more products in order to fill that valley that was created when I removed some C from it. So this is also going to shift right. Okay. Scenario 3 is I'm going to increase my temperature. What happens there? Good, Josh. So when we increase our temperature, we're also going to shift towards the right. If we look at delta H, it's positive. That means we have to go put that delta H or put that heat into the reaction. So we need that at the start of the reaction, like a reactant. So it's like heat plus A plus B is in equilibrium with C plus D. So if we increase heat, it's the same thing as increasing a reactant. And so we're going to shift to the right to create more products. Yes, yep, Casey, that's correct. If we were a negative, if it was a negative delta H, right, then it's like a product, we're producing it. So I guess we'll kind of just do a dotted line here. Right, so if we have A plus B going to C plus D plus heat, right, this would be delta H is negative. If we increase heat on this side, we have to shift it to the left. Okay, does that make sense for an exothermic reaction if heat is increasing? Okay, cool. Yep, exo and endothermic is only for temperature. So if volume is increasing here, so I guess if volume changes, period, you have to determine how many moles of gaseous things you have on your reactants or you have on your products. Okay, so I can just hold here for a second. I'm gonna explain it, then I'll show you. So if we're increasing our volume, right? If we have, let's say, just like this sized container right now, and we're going to increase it to this size, we now have more space in that container. So if we have more space, we want that pressure to stay the same. And in order to keep that pressure the same, we have to increase the number of gaseous products we have. So we have to shift towards this side that has more gaseous products, and that will increase the amount of pressure because now there's more gaseous things in our container. So if we were to look at it where it's, let's say, do another dotted line, right? We have 2A gas plus B gas goes to 3C gas and 4D gas. Okay, if we were to increase volume, which side do we shift towards, the product or the reactants? So we're going to shift towards the products. We're increasing volume. So now, I guess, so we have, let's see, we have this shape, and we have 6 particles in our container, right? So the pressure is 6 right now. If we increase our volume, so now we have this bigger circle. When that first initially increases, we still have those 6 particles in our container, but we want that pressure to stay the same. And so in order for the pressure to stay the same, we have to produce more gaseous particles. So we want to have more things in our container to keep that pressure the same. This side has more gaseous things, so we're going to shift towards the products to increase the number of gaseous particles we have to increase the pressure of our container. Does that make sense? And when we say, okay, and then we say shift, and that just means that the reaction is going to proceed like in towards the products or towards the reactants. Like right now, it's happening at equilibrium, seeing both back and forth. But we're just going to have a favor for producing products rather than reactants. Yes, awesome. So if it was the other way around, if we said, okay, this is 3A and 4B goes to goes to C. And then if this was D solid, right? If we're increasing volume this time, we're now going to shift towards reactants or produce more reactants because we have an increased in volume. We need to increase the amount of pressure again, or return back to that pressure we had before. Does that make sense? We see that for volume changes. Yep, this is only for gas. They will only ask you a volume change about gas. Yep, so you can add the total number of moles of gas. It just depends on what the question is asking, Isaac. If we decreased our volume, then the equal and opposite thing will happen, right? If we increase our volume, we want to go towards the side with more gaseous particles. If we decrease our volume, we want to go to the side with less gaseous particles. So it really just depends on what the reaction is or what the question is asking for. any other questions on Le Chatelier's principle and what it means to disrupt equilibrium and anything like that? So Daniel, this just relates to pressure in terms of at equilibrium, your container will have a certain amount of pressure. And now we're changing equilibrium by either decreasing that amount of pressure or increasing that amount of pressure. And so in order to return back to that equilibrium pressure that we wanted, we either have to make more products or make more reactants. Okay, anything else? Okay, we can talk about equilibrium now. When we talk about equilibrium, what letter do we usually talk about? Is this K uppercase or lowercase?
It's uppercase, but lowercase. Wait,
Good. So you have an uppercase K is going to be equilibrium. What is lowercase k? Good. This is your rate constant. Okay. So, right, this will be easier on your exam because it'll be an actual uppercase K and an actual lowercase k. You should be able to tell the difference. But for right now, I'm just going to hope that my K is big enough where you can convince yourself it's an uppercase. When we write an uppercase equilibrium, if we have this product or this chemical reaction, what is K here? How would you write it?
wasn't it that products of a reactants concentrations with the exponents?
Awesome. So you're going to do your products over reactants. K is always products over reactants. And you use the coefficient in the front as your exponent. So you would have your reactant C to the third times D on the top over A squared times B. Okay, and that would be K. Questions on K? Just generally setting it up. What can go into K? What states, I guess, or phases can go into K?
Wasn't it gas factory?
Yep. Okay. Yep, coefficients become your exponents. Solids and liquids, you don't include. So if we have We have this reaction here. What is our K for this reaction? Sorry, this is a 3. Awesome. Awesome, great job. Okay, so we have HO3 plus NO3 minus goes to HNO3, or divided by HNO3. What is HNO3 classified as? What can we call that? Yep. I guess in terms of yep, I like that last one. This is an acid. What kind of acid? Good. This is a strong acid. So does that mean it fully or only partially dissociates? Okay. What strong acids do we have? We said HNO3. Yep, HI, HCl, HBr, H2SO4. There's one more. Good. HClO4.
Need to memorize those.
Yep, you should know your 6 strong acids, and then you should know your 6 strong bases as well. Does anyone know their 6 strong bases?
I think one of them ABR and ABR.
Yep, so we have NaOH, lithium OH, and potassium OH. We have calcium hydroxide, strontium hydroxide, and barium hydroxide. So you should memorize your 6 strong acids and your 6 strong bases. On the periodic table, I always know the 6 strong bases because they go like this. So you have like lithium, sodium, potassium, calcium, strontium, and barium. If you look at them, boop, 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 on your periodic table. Yep, and this will all be posted. And then your 6 strong acids, you just kind of have to know. HCl, HBr, HI go down the periodic table in your halogens. But then the NO3, SO4, and ClO4, I do not have a way to think of or remember them. I've just kind of memorized them over the years. But those are 6 strong acids that you should know. If you know your 6 strong acids, anything else is weak. I would memorize the 6 just in case. It's just one extra. And I mean, I know it's one extra on top of everything else you need to know too. But it's in between calcium and barium, so it also counts as a strong acid on the periodic table. But I always know 6 strong acids, 6 strong bases. So I would memorize those 12. Okay, all of these will always fully dissociate. Anything else will only partially dissociate. Questions on equilibrium are the plus or minus acid. I don't know what that question means. So, okay, so that's a good question. That's a really good question. So let's look at this one again. So we had HNO3, H2O, HNO3 minus, and I'm sorry, H3 plus and NO3 minus. Okay, so what did we classify our HNO3 as? Good, this was a strong acid. A strong acid means that it has an proton to donate. So your H plus, or this H here, is your proton. So it is a proton donor as your like definition of an acid. Okay. So your proton donor means that that's going to be your acid. Your conjugate base is the resulting compound after you lose that proton. So what would be its conjugate base here, right? It's the same element or the same compound, just minus 1 H. Good. It would be this. Here. Okay. The minus is saying it gave up its proton and now it has one less proton available. So that's its conjugate base. Your base means that it is a proton acceptor. So you can put a base on it, right? Or can accept a proton. So if your HNO3 is your acid, what does that make your H2O? What would you classify the H2O as? I like base, but is it one of the strong bases we just talked about? Nope. So is this a weak or a strong base? This is a weak base. Okay. So what does that make the H3O plus? Good. This is a weak acid. This is a weak acid and it's your conjugate acid. And it is a weak base, Brock, because it's not one of the 6 strong bases we talked about. You have those 6 strong things, acids and bases, and then everything else is considered weak. Yep. Okay, so you will always have, yep. So bases can change to acids when they gain an H, right? So your opposite, you will always have conjugate base, or you always have a base and an acid paired together on either side. Conjugate is not the same thing as weak. Conjugate means it's like partner, almost, right? So you always have an acid and a base pair. So if you have an acid on the left, you have a conjugate base on the right. If you have a base on the right, you have a conjugate acid on the left. Okay, we can do another example showing that. So we have NaOH and H2O. This results in I'm sorry, let me do this. We have NH3 and H2. Again. Okay, so let's label these. It's going to be a little bit harder to see what happens, but let's label these. Can anyone tell me what they think the acid and the base is in our reactants? Okay, so they're both weak. I like this one. This is something weak. This is something weak.
Okay, right. I was just saying it, and it is acid if it like doesn't like that would make sense, but other filling it on that.
So nope, the strong base will not always be negatively charged. So again, we have to think about what it means to be an acid and a base. Your acid is going to be a proton donor, and your base is going to be a proton acceptor. So which thing here accepted a proton? Which thing gets another H in its compound? NH4, right? NH4 is now one more proton higher. So what is its? So if that gained a proton, what does that mean it is?
That big.
That's the base, right? So your NH3, the thing that's gaining the base, or that's gaining the proton, is going to be your base. Your NH3 is a proton acceptor. So that's your weak base, making your NH4 plus what?
Conjugate acid.
Yep, awesome, great job. All right, this is going to be your conjugate acid. So what does that make water here?
Acid.
Good, this is your weak acid. What is the OH minus?
Conjugate.
Awesome, this is your weak conjugate base. Okay, do we see how we determine which one's acid and base and its counterpart between its conjugate acid and base?
So do we always go from left to right? At that time,
Yep, so if you're determining if something's acid or base, you always want to go, and then its counterpart of conjugate acid or base, you always want to go left to right. So Zach, you tell me, is NH4 weak or strong? Yep, it would be weak. Right? It's not one of the 6 strong acids we talk about, so it will be your weak. Yep, so your acid loses a H, base gains an H. Your conjugate acid is your base plus an additional H, and your conjugate base is your acid minus H. Yep, so your arrow this way just means one direction, no equilibrium. Your double arrow is at equilibrium. If something is product favored, this means equilibrium, I guess, at equilibrium, concentration of products is a lot higher than concentration of reactants. Does that answer the most recent questions that popped in? Okay, awesome. Okay. We have 30 more minutes. I see something for intermolecular forces. Do you want to go over that, or do you or is there anything else you want to see in the last 30 minutes? I can start on intermolecular forces and then if anything else comes in. Okay, so for intermolecular forces, you always want to know that London dispersion forces are in all molecules. These are your LDFs. Whether this is polar, non-polar, anything like that, London dispersion forces will always be present. Hydrogen bonds. Must have an HO, H N or HF. Dipole is between two polar molecules. And these are weaker than hydrogen bonds. Will never have an induced intermolecular force in a pure substance. I think those are your big things for intermolecular forces. Any questions on intermolecular forces, or what questions do we have about them?
Do London dispersion forces have another name?
Um,
Because I remember something
No.
from class about that.
I think most of them are just called London dispersion forces.
Okay,
Or LDFs is what I usually see them as.
all right, thank you.
I would ask, so I think Nasata was talking about dipole, induced dipole, the molecular forces, and induced dipole, molecular forces. Are those both London dispersion forces, or is only one of them London dispersion forces? Seems like there's like one type of force that we didn't like talk about much, except like mentioned.
Yeah, so your London dispersion forces will be in any molecule, whether it's polar or non-polar, it'll always have London dispersion forces. And yeah, so dispersion, LDF can also just be dispersion forces. And then your induced dipole is like when a polar molecule comes near a non-polar molecule, causing a dipole to happen. And ion dipole would be it's like if you have Na plus, right? You have an ion and it comes near a fluorine and carbon molecule. Your fluorine is going to be partially negative and partially positive for your carbon. So your positive charge will line up with the negative, and then your positive will go away. So then it's causing, and since that negative and positive are close together, it'll cause a larger dipole in your substance. Does that make sense?
That's true.
I wouldn't worry too much about the induced intermolecular forces. I think if you remember that all your molecules will have London dispersion forces, and then your hydrogen bonds have to be HO, HN, or HF directly, and your dipoles with polar bonds, that'll be the most important. So your strongest, or so you're like, in order, so your hydrogen bonds are going to be your strongest, just for like the three that I mentioned, and then dipole, and then LDF. Your ionic bond is stronger than H bond. Gage, you should be able to see that. If you click on your exam in the like exams tab, you should be able to pop up to your old exams. Yep. Any other questions on intermolecular forces? Yep, ionic bonds are between a metal and a non-metal. So like a sodium and a fluorine, or a sodium and a chlorine is a ionic bond. Ion dipole will be higher than your hydrogen bonds. The sheet that has all the equations for the final should be on your mock exam. I guess she just posted that. I didn't know that it was posted. But that should have your formula sheet that you would get for a mock exam, or for a final exam is in the mock exam. So then Logan, for a example. Okay, so what IMFs are present in the pure substance of the following? And you have that molecule there. Yep, so it's going to be LDFs. Anything else? Yep, and then dipole. Do we have any hydrogen bonds? Nope. Your carbon and fluorine here, right, your fluorine's attached to a carbon, no hydrogen, and then your oxygen is attached to a carbon here, so no hydrogen directly there. Yep, no ionic bonds either. And the dipole is going to come from this is going to be polar, and then these bonds are also polar over here. So those are all have polar bonds. Help with IMFs a little bit? Okay. So you tell your bonds are polar based off of the differences in electronegativity. Okay, let's talk about Gibbs free energy. This, does anyone know what value, like positive or negative, we want delta G to be?
One that's negative, you want the reaction to be symmetric.
Yep. Want negative to be spontaneous. Does anyone know what the formula for delta G is? Like what relates our enthalpy and entropy together?
Delta G equals delta H minus T delta.
Awesome. Okay, that should be on your formula sheet. And then this is also something that I used to do, especially when it came to physics, and then I applied it to chemistry as well. I would always look at my formula sheet before an exam and just kind of like map out where like each type of problem is, right? So like if you're looking for a calorimetry problem, then you want to look for MC delta T. So if you look at MC delta T, you're like, okay, that's calorimetry. If you do delta G, then you're like, okay, here's delta G is equal to delta H minus T delta S. You know where that is on the formula. And then you can say, okay, that's my free energy equation. And kind of annotate a formula sheet so you know, okay, this is what I'm looking for when I have this type of problem. Same thing with like energy of a wavelength or a photon, looking at those and saying, okay, what do these letters mean in all of my equations? And all of that fun stuff there. Okay, so that was also something I did, and I found that super helpful. And then also keeps you a little bit more aware of where equations are on your formula sheet, and then you don't have to spend as much time looking for them, which I think is also very helpful in a time crunch situation. Sorry. So this is going to be your free energy. This is going to be your enthalpy, and this is going to be your entropy. What do we want T to be in terms of equations? Good. We want this to be what does the world prefer delta H to be in terms of positive or negative?
Did it even have a preference for that delta S?
Yep. So we want this, or you'll say world prefers to be negative. And for entropy, the world prefers to be positive. Okay. Your reaction becomes spontaneous when delta G naught is equal to 0. Yep, you want your reaction to be spontaneous. So want negative means spontaneous. And reaction at equilibrium, delta G is also equal to 0. So delta H naught is equal to T delta S naught. Questions there? You can solve for delta G the same way you solve for delta H or delta S in terms of the sum of the products minus the sum of the reactants. And the most important thing to note is that you want it spontaneous when it's negative. Any other questions on Gibbs free energy? Okay. And then I think the last thing I saw that we might have time for is molar solubility. Or this is your KSP. And this is yours, or your solubility product. Delta G naught is at standard temperature and pressure. And then your delta G is at any other condition, so non-standard conditions. So your solubility product is for something like magnesium chloride dissolving in solution, creating some magnesium plus ions and some chlorine minus ions. I believe the temperature is 25 degrees Celsius. So then it would be 298 Kelvin. But if I'm wrong and it's actually 273, just let me know. But I believe STP is 1 ATM and 25 degrees Celsius. So then that's 298 Kelvin. Okay, so your solubility product is going to be when things that we think are, it's 1 ATM and 0. Okay, cool. So this is 0 degrees Celsius, which is 273 Kelvin. Thank you, Casey. So for solubility product, this is saying that things that we thought to be insoluble are actually soluble. Oh, I don't know. Okay, I'll email Dr. Altemos and I'll ask her just to make sure. I'm pretty sure it's 25 degrees Celsius and 298. But I'll email her just to make sure. "25 degrees Celsius is room temp, so I think that's usual standard temperature and pressure. That's what I was thinking of, Casey. So I thought it was also 0. But I'll email Dr. Altemos, and then when I post everything, I'll let y'all know what it is. I don't want to tell you the wrong information, but I'll make sure I change it in these notes before when I get it, when I get back. But it should be the same as gas laws, Casey. STP should just be STP at all times. Okay, so quickly in 10 minutes, molar solubility is when we think that something was usually insoluble is actually now soluble. So this is like that bottom half of that solubility chart you get for your formula sheet. We're saying that some of these do actually precipitate and do actually form product. We thought that they did not form any product, but sometimes they do. K and S cannot go into your equilibrium. So KSP is just always going to be your products. Okay. You can find your solubility product based off of like X in an ice table. So when we look at an ice table, we have our initial, our change, and then our equilibrium. And this is where some of your like homework problems come from. So we have just your reaction. You have magnesium chloride. And we have magnesium 2 plus and 2Cl minus. Solid does not matter, so we don't even care about it. Initially, you will always start with 0, right? You just have some magnesium chloride solid that you're going to put into your solution. So before you even start the dissolving process, you will have 0 and 0 of each of them. To find your solubility product, or that S, you don't know how that's changing by, so that's going to be your X in your change table. If magnesium is changing by plus X, right, we're forming some magnesium. How much is chlorine changing by? Good, this will be plus 2X. So at equilibrium, our concentrations are going to be X and 2X. Right, these are concentrations at equilibrium. So if we plug it into a KSP, we would say that we have X and 2X squared. So your total is 4X cubed, because you have to square the 2 and you have to square the X, and then also multiply by an additional X. And X here is your solubility product. What questions do we have? Okay, so good question. So it's either going to be plus or minus if something is being used or formed. So if you are producing a product, then it'll be a plus because you need to make more of it. But if it's a reactant and you're using it up, then it would be a negative. So for this one, we don't have any of those ions before we dissolve it. And so then it's going to be a plus for your magnesium and your chlorine because you have to form some of those ions. Does that make sense, Anthony, for your question? Okay. And then Isabella, for this being squared, your KSP, so your actual equation is this this magnesium chloride goes to magnesium and 2 chlorine ions. So this 2 here becomes this square up here. And so when you plug it into your KSP value, you need to keep that square from the original equation that you had. Does that make sense? Okay. And then Gabriel, KSP is the equilibrium of the solubility product. So like the actual value of X is the solubility product. KSP is just the term we give it for the equilibrium of your ions in solution.
So KSP is equal to plus 2.
KSP is equal to plus 2. Say that one more time.
KSP equal to 4x².
Yes. Yep. So for this one, KSP is equal to 4x cubed. If we had a different salt, so let's say it was, oh, I don't know, things that are insoluble off the top of my head. But let's say, I'll just make it up. Let's just say it's AB3 solid. What is this going to break down into? If A is, let's say this is A positive, how many B's do we have? Yep, so it'd be 3B minus, this would be aqueous, this would be aqueous. If we set up our ice table, do we care about our AB3 solid?
No.
Nope, so we don't need any of this. What's our initial concentrations of A and B minus?
0.
What's going to be our change?
So X
This will be plus
and
X.
3X.
Yep, and plus 3X for B. So equilibrium is going to be X and 3X. So KSP for this one, what goes in for A?
X.
X.
Good.
And then what goes in for B?
3X and that all this.
Yep. Good. 3X cubed. So KSP here is X times 9X cubed, or not 9, 27, excuse me. 27X cubed. So KSP is 27X to the 4th. Yep, coefficient and power are the same. Does that make sense how that happens? You will probably only ever see like the 4X cubed or the X squared is my guess. But that's like another example of that. Okay, does anyone have any last minute pressing questions they want to see in the last minute? Yep. So if there was an additional like solid that was produced, you just wouldn't include that in your KSP. And then it would just be whatever is aqueous you would include in your like product or whatever. I will post, yes, I will post this under the mock exam stuff. So I'll have all of this information. Dr. Althamos has posted a mock exam. And so I'll post all of this information in the mock exam as well. I will also make an announcement where it will be housed there as well. I was a biochem major in undergrad, and then decided to be a chem PhD. So, entropy is going to be disorder. So that's your molecular motion. So like how quickly things are moving. And then your enthalpy is your heat. So like how hot or cold things is, and if a reaction requires energy or if a reaction produces energy. And then the change for your KSP is going to be based off of your coefficient and then your X value. So whatever the coefficient is in front of your product or whatever is changing, it'll be that coefficient plus X, or that coefficient and then like or minus X, something like that. Did that help, Adrian, with how we find the change? Okay, cool. Alrighty, well, since it's 101, I will end it here. I have a whole day of hockey ahead of me and making your review, your answer key, finishing up that answer key. But I want to say good luck and thank you very much for a wonderful year. I hope this helped ease some nerves today. This will be posted along with any notes we took today. And if you have any questions within the next couple of days, please send me an email. I'm happy to answer them. I will get back to you. And have a wonderful summer. I will see you on Tuesday. Thank you for being great students. Thank you for allowing me to be a TA for y'all. It's been very fun. And thank you for giving me this experience. If you ever need anything after class as well, whether that be recommendation letters or just life advice in general, I am always an email away. And I will hopefully be graduating around the same time y'all will. So good luck and have a great rest of your weekend. Thank you again so much.